Welcome back to Aurora Tech Channel. Today, I'm going to test out the AnyCubic Kobra 2 Pro, which is based on the AnyCubic Kobra 2 in terms of hardware, with some extra upgrades. Most importantly, it runs Clipper instead of Marlin. It priced at around $300, so let's take a closer look at what we can get from this AnyCubic Kobra 2 Pro. This is a bed slinger with a print volume of 220 by 220 by 250, or a typical Ender 3 size. The motion system uses steel wheels on the X and Y axis. When moving at a higher speed, they won't wear out like regular palm wheels. For the Z axis, it uses palm wheels with dual lead screws synchronized by a timing belt. The extruder is a 4:1 gear ratio dual gear direct extruder. The heater block is volcano style with a larger heating zone that helps melt filament faster. The Y-stepper motor is a NEMA 17 48mm motor with more torque and power to move the bed faster. The part cooling fan is a high RPM 5020 blower. The airflow is 6.1 CFM, which is almost double that of a regular 5015 blower. The fan duct has been upgraded from a 3D printed part on the Kobra 2 to an injection molded part. There's a silicone block at the rear of the print bed, which is used to wipe the nozzle before setting the Z offset at the tool height gauge next to it. This is similar to the tool height sensors on an auto tool changer CNC machine, which sets the Z offset automatically. There are no manual leveling knobs under the bed, so it relies solely on the inductive auto bed leveling. For other features, like a 4.3-inch color touchscreen, a Clipper motherboard with a Cortex A7 chip running at 1.2 GHz, TMC2209 stepper drivers, and a Realtek Wi-Fi chip. The print surface is a single-sided textured PEI spring steel sheet. It has belt tensioners on both the X and Y axis, a filament sensor, clean cable management with a single ribbon cable, and a 400-watt PSU. Rather than a single micro SD card slot like on the Kobra 2, there are 3 USB ports at the front of the printer. This allows you to use a USB drive for complete offline printing and potentially lets you use a webcam for remote monitoring or for you to connect to other devices through future firmware upgrades. I would like to thank AnyCubic for sending me this machine to review and for sponsoring today's video. With that, let's get started. The packaging comes with laser cut foam and all parts are well protected. We have the base, the gantry, a 4.3-inch touchscreen, the print head, a filament holder, a power cord, and some tools. Putting this machine together will take around 10 to 15 minutes. Put the gantry on top of the base and secure it with the 4 long screws. Mount the print head on the X-axis and secure it with 4 M3 screws. Use the remaining 3 screws to secure the touchscreen at the right and snap the filament holder onto the left of the machine. Connect the limit switches and the stepper motor cables, flip the switch to match your local voltage, and the machine is now ready. Once the machine is on, it will start with a setup wizard. Select the language. As this machine supports cloud connection, if you prefer using that, you can connect to your local Wi-Fi and register a cloud account. However, when I received this machine, their cloud service was still under development, so I chose to skip it. Next, it will perform a self-test and require the insertion of the USB drive that came with the machine. After that, it will home the machine, heat up the nozzle, and move the print head to the back of the print bed to wipe off the filament residue using the silicone block. Then, it will move to the tool height gauge to automatically set the Z offset. This is followed by a 25-point auto bed leveling using the inductive sensor. It will then calibrate the input shaper, beginning with the X-axis. Next, it will use the same accelerometer inside the print head to calibrate the Y-axis. With the setup completed, it will ask whether we want to print a model. Since I have no idea what it will print, I will select No and manually choose a model from the sample Gcode. I'll then load PLA filament after selecting preheat PLA. Once the temperature reaches 210 degrees Celsius, I will extrude 100 millimeters of filament. I'll start with a 27-minute Benchy sample Gcode. The AutoZ offset was set to -1.93. I'll keep this setting to observe its printing performance. While some filament residue still sticks to the nozzle, I think it would be better if the machine used the silicone block to wipe the nozzle before every print. However, I won't remove it and just let it print. The first layer is printing at around 80 millimeters per second, which is notably faster than other fast printing machines. When conducting a sound test with the meter positioned about 1 foot away from the machine, the sound level is around the mid-50s, which is pretty quiet for a fast bed slinger. The print finally finished in 27 minutes and 40 seconds. The surface appears quite clean. There is a slight amount of stringing and cooling issues in the middle, and it's more noticeable from the back. At the front, 2 small blobs are present. I'm not sure if this is coincidental, so I printed 2 more models. All of them have the 2 small blobs in the exact same areas. To determine if the issue was due to the sample Gcode or the printer itself, I will use the Prusa Slicer with the printer profile that came with the USB drive. The default PLA profile is using a 0.2mm layer height, with the first layer set to 0.25mm. The top speed is 300mm per second, while the external walls, top and bottom are adjusted to slower speeds accordingly. However, the first layer keeps a speed of 80mm per second, which is relatively fast. The acceleration settings range from 5,000 to 20,000 for infill, which is an aggressive approach for a bed slinger. When printing at a 0.2mm layer height, the estimated print time is 29 minutes. I will save the slice file to the USB drive and start the print. The print finishes in 29 minutes and 52 seconds. The print quality is also similar to the sample Gcode, with a clean surface and minor stringing. The cooling in the same area remains imperfect. However, the previously observed blobs at the front are no longer present, so the issue could have been caused by the sample Gcode. With this resolved, we can proceed to conduct further tests. Now, I will print an infinite cube as a clearance test using VOXELPLA Pro. Once again, the first layer prints at 80mm per second. Although there's not significant squishing, the bed adhesion appears to be strong. The cube's clearance is not perfect, and it requires some bending to move smoothly, but overall it's functional. Next in line is the number slider, which demands even more clearance than the infinite cube. There is some filament residue left on the first layer, but I will just leave it and see if this will have any impact. The print finishes in less than 2 hours, which is the fastest time for this model out of all of the latest fast printers. A few tiles needed to be pulled apart, but the majority of them worked well, and the slider is relatively smooth. Then, I will conduct a retraction test using my Honeycomb box, which has tiny patterns on all sides. It's interesting to see the first layer print so quickly, while still having good adhesion on the print surface. The print finishes in 1 hour and 36 minutes. Other fast printing printers typically take 2 to 2.5 hours to complete this print. Surprisingly, the Kobra 2 Pro managed to print even faster and achieve pretty good results. Upon comparison, this $300 Kobra 2 Pro is the fastest and one of the best in terms of results with other machines at higher prices. Up next, I will be printing one of my favorite models, the Suzuki Jeep. Since this print includes some overhanging parts, I'm curious to see how well this super high-speed bed slinger can handle them. I will use VOXELPLA PLA Pro for this print. The model finishes in just 2 hours and 15 minutes, making it the fastest one I've printed so far. The results still look decent. Let's compare it with another print that took 9 hours using a Marlin printer. The PEI texture on the bottom makes it a bit challenging to compare, but take a look at the front, and I don't think their differences are that obvious. If I don't mention which is which, you'd probably have to guess. The only area that doesn't match the quality of the 9-hour print is the overhanging part here. This suggests that more rapid cooling might be necessary for this unsupported line that printed in the air. Following that, I will print the Robo Alpaca model from Prusa using the same default PLA profile. This model's estimated time is only 3 hours and 9 minutes, which is notably faster than other fast machines that require 4 to 5 hours. The infill of the body is being printed at 300 mm per second with a 20K acceleration, which significantly contributes to saving time. Despite the fast printing time, the print quality remains quite impressive. This is the model from 4 different angles. Let's compare the result with other machines. Against the $399 AnkerMake M5C, the print quality is similar. However, considering that the Kobra 2 Pro completed the print in half the time, the Kobra 2 Pro is the winner. When comparing it with the Creality K1, the Kobra 2 Pro is a clear winner in terms of both print quality and speed, as the K1 was using an early version firmware during this print and the input shaper wasn't performing too well. In comparison with the P1P, not only does the P1P have a cleaner surface, but the layer lines are also better. The P1P took an hour longer, but I will still pick it as the winner. Finally, when put up against the Prusa MK4, the MK4 print quality is the best so far. However, its printing time is also the slowest among all the latest generation printers. Next, I will try some Eryone TPU to print a simple card wallet. The print speed was set to 80 mm per second, as TPU can't be printed that fast. The extrusion is perfect and I have no complaints. I wonder if I can push it even further, so I'll try 100 mm per second. This was not successful, so I would say 80 mm per second is probably the maximum speed you can print with this machine for TPU. Then, I will print a PETG phone stand. As PETG won't stick that well at a high speed, even though the extruder in hot end can melt it fast enough, I set the volumetric speed limit to 10 mm³ per second, which is around 125 mm per second. This model took a little over 2 hours. The surface is alright, though it's not as clean as other PLA prints. But as I normally just use PETG for functional parts, printing PETG at 125 mm per second on this machine seems to work just fine. Next, I will try some ABS. Typically, I apply glue when printing ABS, but let's experiment with printing it directly on the bed and observe the outcome. The crate finished in a little less than 3 hours. There's a small amount of warping at the corners, but it does appear to perform better than regular ABS. Unlike other crates I printed on an open frame printer, the layers didn't experience any cracking. Overall, the result looks quite good. As the maximum nozzle temperature of this machine is 270 degrees Celsius and it only comes with brass nozzles, I won't print any polycarbonate or abrasive nylon carbon fiber, but I will print some nylon. I will reprint the card wallet. I will print at 125 mm per second without using glue, but after a while the print warped. This roll of nylon has been open for a while, and I didn't put it back in my airtight filament box, so it absorbed quite a lot of moisture. I will apply some glue to the bed and see if it's going to print better. While this prevented warping, the layer looks like a textured finish, which is unexpected. But it was clear that the nylon filament has absorbed too much moisture. So, I used my new Sunloo filament dryer, which can reach up to 70 degrees Celsius, and dried it for 6 hours. After that, I reprinted the model. This is what nylon filament is supposed to look like when it is dried completely. When compared to the previous prints without properly dried nylon, the final one looks much better. Not only does the surface look much better, the inside is also smoother and doesn't have stringing. Finally, I will print a single layer PLA sheet to test the bed leveling. The AutoZ offset is set to -1.93, and I have adjusted it to be slightly lower at -1.98 to print this PLA sheet. The left side is a bit too low, so the leveling algorithm is still yet to be optimized, but the entire sheet can be removed without any other issues. While this first layer may not be perfect, it should be good enough for most 3D models, even larger ones. Okay. Let's talk about the pros and cons of this printer, starting with the pros. 1. The motion system works well. The steel wheels on the X and Y axes work better than palm wheels, as they won't wear out when printing at high speeds. 2. The extruder and hot end effectively maintain a rapid extrusion and filament melting rate. For most prints, it operates at 300 milliliters per second for infill, and I haven't seen any under extrusion. I can also print TPU at a slightly faster speed of 80 milliliters per second. 3. The input shaper works well even with one accelerometer on the print head. The surface quality is very good and is even better than some other machines at a higher price point. 4. The PEI sheet adheres effectively, which is evident from the successful and aggressive first layer at 80 milliliters per second. I didn't encounter any adhesion issues even when printing the first layer at this speed. Printing ABS without using glue still yields good results, which is quite uncommon for an open-frame bread slinger. 5. As all of the hardware is solid, including the motion system, robust extruder and hot end combination, and strong part cooling, the print speed is one of the fastest out of all latest generation clipper machines. The quality is also presentable. I won't say it's better than the BambuLab X1 Carbon, but when compared to all other clipper bed slingers I've tested so far, when they're all printing at the same speed, this machine has the best print quality. Now for the cons. 1. This machine comes with a Realtek Wi-Fi module. With Clipper firmware, it should be able to run the standard Moonraker plugin that allows you to print directly from any slicer over your local Wi-Fi network and use the main Sailor Fluid web interface to control the printer and monitor print jobs. However, AnyCubic chose to use their own cloud server and mobile app. In fact, most people in the 3D printing community don't prefer to upload their print file to a cloud server, which you can see from how many Creality and even BambuLab users were trying to get rid of their cloud service and print directly over their own local network. As their cloud service will not be available until September 15th, I wasn't able to test it in this video. 2. The nozzle wiping silicone block is a nice feature, but it's only used before using the sensor to set the Z offset. It would be even better to clean the nozzle before every print starts. As you can see in the video, I have several prints with some filament residue remaining on the nozzle, and the residue was then wiped on the first layer. Considering that the necessary hardware is already in place, it would be better to make more effective use of it. 3. The nozzle is similar to a volcano nozzle, but the part that makes contact with the heat break has a smaller diameter. As a result, despite having the same threads and length as a standard volcano nozzle, it won't work as it'll leave a gap between the heat break and the nozzle. It would be preferable if the printer just used standard volcano nozzles, as they are not expensive and easy to get. Furthermore, the maximum temperature capability of the hot end is limited to 270 degrees Celsius. It would be better to include an all-metal heat break that can print at 300 degrees Celsius, so the printer can print with a broader range of filament. 4. The slicer profile is available in the AnyCubic Slicer, which is a skin Prusa slicer, but it only comes with a PLA profile. It would be better to include other common materials like PETG, TPU, and ABS as well. They have also made a profile for the original Prusa slicer, but still it only includes a single PLA profile. 5. The bed leveling algorithm may still need to be improved. The leveling is still usable on most prints, but it could be better. The Z offset adjustment is in increments of 0.05, which may not be enough. I think the first layer test will print better if I can move the nozzle up around 0.02 or 0.03 millimeters. In conclusion, the print speed and print quality of this printer are exceptional. The print quality is still pretty good when printing at a super aggressive speed of 300 millimeters per second with a 20K acceleration on a bed slinger. The motion system, extruder, hot end, and part cooling are all working well. For some models that require extra cooling, you may need to lower the speed in the slicer profile, but the overall performance is better than other fast printing bed slingers and exceeds my expectations. The only drawback is probably the cloud feature. I would rather use the standard Moonraker plugin to print directly from the slicer within my local network and use the Mainsail or Fluid Web interface to monitor the print. If AnyCubic will release a firmware that comes with a standard Moonraker API that allows you to use any slicer to print directly over your network, this would definitely be the best budget fast clipper bed slinger available. That's all I wanted to share about this machine. If you found this video helpful, please give it a like and consider subscribing to our channel. Thank you for watching and I will see you next time. Please give it a like and subscribe.